students, very warm good morning and welcome to the digital classes. Dear students, as yesterday we have finished our chapter 5, that is states of matter, in which we have done last topic, that is liquefaction of gas and the properties of liquid. So today I'm going to summarize the whole unit, or I can say the recapitulate the whole unit, so that all the topics that we have studied in this chapter will recapitulate in your mind. So dear students, the chapter started with the introduction of matter, in which we studied that all the matter that occupy space and have mass is known as matter. So there are basically three states of matter: solid, liquid and gas, in which in this particular chapter we will be talking about gases and solid liquid state. So first we will talk about gases, so in which we studied that basic properties of gases, in which gas can exert pressure. We studied that gas are exerting pressure. Gas don't have fixed shape and volume, and it acquires the shape of container. They are very low in density. Gas are highly compressible. Gases exert pressure on the wall of surfaces, and they mix evenly and uniformly without any mechanical aid, that is called diffusion. So these are the basic properties that we have studied. Even we studied that basically non-metal or element that exist as a gases under normal condition. There are total 11 elements that exist as a gases: hydrogen, helium, nitrogen, oxygen, fluorine, neon, chlorine, argon, krypton, xenon and radon. After this we have studied the gases laws. What are gases laws? It is the laws that tell us about with the change in pressure, volume, temperature and number of molecule, what is the derivation. So there are basically the following laws: Boyle's law, Charles law, Avogadro's law, Gay-Lussac law, Dalton's partial pressure law and kinetic gas theory, in which Boyle's law, Charles law, Avogadro's law combined and it form ideal gas law. These are the basic gas laws, in which Boyle's law is also known as pressure volume relation, where volume is inversely proportional to pressure and volume is equal to K into 1 upon P, whereas PV is equal to K. So we got one formula, that is P1 V1 is equal to P2 V2. Now there are some numerical related to this formula. Second law is Charles law, which is called volume temperature relationship, where volume is directly proportional to temperature. As you know that as we increase the temperature, volume will increase. Okay, so we got the value V is equal to KT, whereas V upon T is equal to K. So we got value V1 T1 is equal to V2 upon T2. Third is Avogadro's law, where volume is related to number of mole. So volume is directly proportional to number of mole, where it's V upon N is equal to K, where value become M is directly proportional to D as compared to density. After this, by adding Boyle's, Charles and Avogadro in combined, we got ideal gas law, which is PV is equal to nRT. Fourth gas law is Gay-Lussac law, which is pressure temperature relationship. With the increase in pressure, temperature will increase. So P upon T is equal to K, where value is coming P1 upon T1 is equal to P2 upon T2. And the last one is Dalton's law of partial pressure, which states that total pressure of a mixture of non-reacting gases is equal to the sum of the partial pressure of individual gases. So P total is equal to P1 plus P2 plus P3 and so on. This is Dalton's law of partial. After this, there is some numerical that is related to these gas laws. So numericals related to gas laws that we did. But if you want to practice, so you need to watch the previous videos and you need to go through the exercise where the numericals are there related to these topics. Okay, after this, after doing gas laws, and we came to know that ideal gas is gas law, in which pressure volume is directly proportional to nRT. So PV is equal to NT, but at rate constant at temperature. So the question was there, what is R? R we need to find out, that we found it is 8.314 joule per Kelvin. So there is a ideal gas which obey that PV is equal to nRT in all condition, all pressure and temperature and volume, whereas real gas are those gases which is behaving like ideal gas only in case of low. Real gas are there in which all gas which follow gas laws at low pressure and high temperature only. So which is basically the major difference between ideal gas and real gas that we have done. All gases which follow gas law at all temperature pressure is called ideal gas. All gas which follow gas law at low pressure and high temperature, this is special condition, low pressure, high temperature, that kind of gases are called real gas. Whereas in ideal gas PV is equal to nRT, in real gas PV is not equal to nRT. Similar way Z is equal to 1, whereas Z is not equal to 1. It means that either Z is greater than 1, then it will show positive deviation, which is the above this normal line, and Z is smaller than 1, that is negative deviation, that is below this normal line. So basically that is called this deviation in line. You can see the ideal gas is this one line is ideal gas, but these all I can say graph, that deviation that is showing the behavior, that is showing the behavior of real gas, in which deviation is there from ideal behavior. Okay, so in case of carbon dioxide, methane, oxygen, hydrogen, nitrogen, these all are real gases which is not equal to, in which Z is not equal to 1. After studying the deviation of real gas, we move for next topic, that is liquefaction of gas. The meaning of liquefaction of gas is in which the gas is compressed and convert into the liquid. There are so many important application of liquefied gas in our daily life, that is like LPG, CNG and liquefied oxygen cylinder in hospitals. These all are example of liquefied gas. It means that where gas need to be compressed, compression will be there at high pressure. So at high pressure and low temperature, and high pressure, the gases are converting into liquid. That process is called liquefaction of gas, and it is very important because in normal condition it is very difficult to transport the gas from one place to another until it will not be liquefied. So this is the chapter 5, and hope so you recall each and everything. Now we will start our chapter 6, that is thermodynamic. So I'm going to take thermodynamic introduction after this. So stay tuned and enjoy the digital classes. Thank you.